Why is the sky blue? How is a rainbow created? We get up, wash ourselves, eat a small breakfast, and commute every day of our lives. In our work, if it's a sunny day, a gorgeous blue sky will inspire us to start moving outside. Work. Or, if it's raining but the sun is still out, you may see a breathtaking rainbow that will make us happy and entertained. Later, following a full day spent in the workplace, we're returning home. We can enjoy a lovely aperitif with a loved one if it's a special occasion. At one of those settings that is charming and has an amazing perspective of the city. After a challenging day, we'll take a nap and savor the moment by taking in a stunning sunset. Some of us will likely choose to leave after dinner and ascend a hill outside of the city to enjoy a magnificent evening viewing stars in the nighttime sky with their partners. Nevertheless, do we ever ponder why the sky changes? Beginning with blue, changing to red, and becoming darker at night? Thank you for visiting KYC News. Please subscribe and click the bell icon. And why does a rainbow only appear when it is raining? Follow if you want to learn more about this. In this video, I take you on a delightful journey through some simple but fascinating, intriguing facts about optics. We need to step back and try to understand these common phenomena before digging into their explanation. To clarify a basic question, what is light? Optics is the primary science that investigates this subject. It was initially created in the 16th century by Isaac Newton. Back then, everyone considered light to be a wave with its own wavelength, the space between two peaks that follow each other, and intensity, the height of the peaks. Two important aspects of light behavior were investigated during that time: reflection and refraction. When a ray encounters a reflective surface like a mirror, the first one occurs, which doesn't allowing something to pass through and reflecting the beam at its original angle of incidence. The second occurrence is typical of non-completely reflecting surfaces. When light moves from one substance to another, its trajectory alters, and the deviation is the two areas' densities are different. Have you ever witnessed what occurs when you point a laser on a water glass? When the beam penetrates the fluid, it bends in a different direction. Later, in the 19th century, thanks to the assistance of the illustrious James Clerk Maxwell, scientists have learned that light is simply a specific sort of electromagnetic radiation with a specific range of wavelengths, between 300 to 700 nanometers, that are visible to our eyes. Actually, though, the only physical distinction between light and an X-ray, gamma ray, or infrared is one of value: wavelength. These radiation types experience the same reflection and refraction effects. For instance, sun rays seem white because they include an equal amount of every observable wavelength, whereas special sodium-fueled lamps are characterized by an orange light as a result of due to the fact that various types of emission are primarily composed of wavelengths around 600 nanometers. Additionally, because of the creation of sophisticated mathematical tools, we're able to more clearly describe things in the final 50 years of the 19th century. A larger variety of light events in a scientific manner. They realized that light comes from various angles, depending on its wavelength of refraction. Knowing this allowed scientists to explain some impacts that earlier physicists like Newton had noted. One of these is very well known. Do you know what Pink Floyd's most recognizable logo is? A prism. Why is it significant? 2. The prism can distinguish between several wavelengths of a brilliant ray. How does it accomplish that? The beam that is directed at the prism goes when it enters the glass. There is a first refraction. When it exits the glass, there is a second refraction. All the various hues follow slightly different routes in space as a result of this double refraction. The spectrum is the division of the original light's constituent parts. Did you know that a similar occurrence is what causes for those stunning rainbows you observe following a rainy afternoon? Are you aware? How are those events explicable? The response might surprise you. We need to ask ourselves this in order to find a solution to this issue. What are the two main conditions that must be met in order for a rainbow to appear? Rain and sun. This is where we begin. The truth is that the answer that can be found in those two terms. Let's begin with the first. Just what is rain composed of? Water. And how do we depict rainwater in a sketch? It can be visualized as an assortment of spheres and various sizes. We can now think about the second characteristic, that sunlight is what causes a rainbow to form. When a sunbeam strikes a water sphere, it experiences a first refraction, a second reflection on the droplet's back, and a final reflection as you exit. This procedure causes light to be dispersed, much like in a prism. The rays will emanate in a variety of directions since the droplets are positioned differently. Thus, when we think of rain as being made up of a large number of water droplets, the rainbow is the result of the splitting of sunlight into its various colors. In addition, another distinct substance allows for the observation of a comparable effect. Have you ever noticed something odd while filling up your automobile at the gas station? If any, when sunlight hits oil patches, the same dispersion causes a little rainbow to appear. We need to define a new phenomenon called scattering before we can continue with other commonplace interesting facts. Scientists learned at the start of the 20th century that light was quantized in the form of termed photons, tiny particles. Immediately, they began to have doubts regarding the presence of the wave, towards a more corpuscular description of light. Hence, with the advancement in quantum physics, a theory that can describe particles more accurately than any other, scientists discovered that every atom exhibits an undulating behavior. As a result, we may state, depending on the circumstances, light can be viewed as either a wave or a particle. This hypothesis allowed researchers to explain how individual atoms interact using radiation. This specific phenomena is also referred to as scattering. The results depending on the properties and size of the atom in the interaction within the wave. The atom quickly absorbs light and re-irradiates it, producing fresh photons. First off, if a particle exists that is significantly smaller than the wavelength of the Rayleigh scattering, after the 19th century scientist, is the name we give to this type of radiation. Lord Rayleigh, a physicist from the UK. One may discover that the power of light dispersion is inversely related to 4. The result of it is blue, which has a shorter wavelength between 500 to 520 nanometers, is significantly more strongly reflected than red, which has a higher wavelength of 700 nanometers, which has a greater wavelength of 700 nanometers. The primary cause of why our sky appears to be blue because Rayleigh scattering describes how the particles in our atmosphere interact. Your answer may have been satisfied by this demonstration, but an accurate observer won't be entirely satisfied with these claims and will continue to be dubious. In reality, it appears that only one question remains to obliterate this definition. Do you realize it? This is it. Why is the sun red? Air is constant. Same and exhibits Rayleigh principles, however there is no sign of blue. Why is it the case? The solution is rather straightforward. After the sun has set, it emerges in front of us at night, and its light must go a wider distance. Then at noon, a layer of the atmosphere, due of the higher power with which blue and green components are emitted, only the other colors are consumed after a specified amount of airborne distance. Orange, purple, and red are still discernible. Continuing with this subject, more queries may ascend to the heavens. For instance, why is the sky dark at night? What happened to our atmosphere? When the sun is not illuminating it, the atmosphere is transparent. I'll attempt to give you a simple example. Ever drove in fog? What occurs when you turn on your headlights? Light interacts with the water vapor in the fog and experiences some scattering. There are beams diffused, and the fog is even more obstructive of our vision. Alternatively, if our headlights are reduced, the fog appears to be less dense. On Earth, the same thing occurs at night. As the sun sets, the atmosphere loses its illumination and nearly becomes translucent, providing a glimpse of the galaxy's black background and stars. The final, but not least consequence that will make you experience complete shock is suntan. Have you ever wished you had a gorgeous tan body in the summer heat? Well, this phenomenon is underpinned by a lot of optics. Let's examine it. In the past, we stated that solar light is white because it is equally made of all hues. As a result, the sun emits more than just electromagnetic visible radiation. In reality, it emits radiation at other wavelengths, such infrared. Visible light has beneficial impacts on our bodies, but other types of light don't have the same advantages. Radiation frequencies that are unluckily bad for our bodies. Even if most of them completely absorbed by our atmosphere, which serves as a shield and supports life on Earth. Some potentially hazardous rays may reach the ground. In particular, UV rays are well known. They could seriously burn our skin and cause damage. Thankfully, our body has excellent protection. Melanin is a substance that protects us from sunshine. It is a natural colorant with the capacity to it can be two different colors and absorb a particular quantity of UV rays. One is brown and the other is red, pheomelanin, eumelanin. The organism begins to produce melanin at a higher rate when sunlight touches our skin, lowering the chance of getting a sunburn. However, how does melanin manage to provide us that lovely tan we enjoy flaunting at the beach? The first of the two primary procedures is the melanin undergoes oxidation, which darkens its hue. In this instance, there isn't an improved future UV ray shielding sunscreen should be worn even if we are completely tanned. On the other side, there is an alternative method of tanning. If the vast majority of rays is UVB, our body overproduces melanin, which results in delayed tanning, which is even more damaging. Then the oxidation one, protecting a skin that has undergone this treatment to tan may be able to withstand UV 3 times more effective than a typical one. In conclusion, there are numerous people around us. Phenomenon that could seem normal and usual yet actually conceal a lot of remarkable things impacts of physics. Most of us probably have never considered the origin trying to come up with a plausible answer, but thinking about a rainbow or a breathtaking sunset science is available to explain these occurrences, and it will continue to leave you feeling every time, I'm shocked and amazed. Here's where the video ends. Thank you for viewing. Everyone, are you intrigued by this subject? Are you astounded by the details of this entertaining? Regular facts? Did you already know how a rainbow forms or why the sky is blue? Do you recall? Ever heard of scattering? Do you have any other questions about optics?
Yeah, yeah.